vai embaixo, desaceleração. Então, vamos dar início ao minicurso. Bem-vindo, welcome, professor Leisa.
Okay, so we have a lot of students. You know that is your first day here. I'm sorry I cannot do it in Portuguese, but I mean, you are also used to receive classes in English, so I think that you will understand. But anyway, feel free to ask me any question during the course. For those of you that you were yesterday in my research presentation, I mean, today and the next days I will go slowly, although I have plenty of things to teach you on emulsion polymerization. It's a broader course that I summarize in 6 hours, so I hope that I will give you a flavor of what emulsion polymerization is, what are the mechanisms, and what are the uses of this polymerization technique to produce polymer dispersions. Okay? So we will start. I have divided the course in three classes, in today, tomorrow, and as tomorrow. So today we will analyze the main characteristics and main commercial polymers and uses of emulsion polymers. I will discuss which are the most the ingredients of the formulation, especially initiators and surfactants, and the role that they have. And then probably I will do this in the first part, and then I will, by the way, I will do 15 minutes class. We will have a break to relax. Okay, it's hot here. To drink a little bit, relax a little bit, and we will start again. I mean, 2 hours is impossible. Okay, so and then I will go to the physical description of the emulsion polymerization, which are the main mechanisms by the polymer particles are formed, okay, and which are the main mechanisms that occur during the formation of the polymer particles. And then I will discuss probably one of the most important aspects of the emulsion polymerization that distinguishes with other polymerization techniques, either the homogeneous or the heterogeneous, like suspension polymerization, which is the concept of the compartmentalization of the radicals and its implications. So you will see this little by little. Here I included bibliography, some books in which I'm based my presentation. Okay, so those are the most important books. I mean, from the mechanistic point of view, the book of Bob Gilbert is probably the best. From the description point of view, the book of Lovell and Lasser. And then in the rest of the books, you will find additional information that I will use during the course. Okay, I assume that you all have already knowledge of polymerization and the book and homogeneous conditions, okay? So because otherwise you will have some gaps, right? But okay. Emulsion polymerization is a technique in which we obtain polymer particles dispersed in water. So basically what we will obtain are polymer particles dispersed in a continuous medium which is water, okay? And these systems are important and were developed for the first time. It's a little bit of history of emulsion polymerization. Were developed for the first time synthetically during the Second World War, because there was a shortage of natural latex. And natural latex, which is obtained from Ebeas brasiliensis trees, is a dispersion of polyisoprene dispersed in water, stabilized by certain proteins. Okay? So during the Second World War, there was a shortage to these natural latex sites, which were out of the control of the Germans and the US. So US and Germany developed or put a lot of money to develop a way to synthetically produce natural rubber, which was the styrene butadiene rubber, which is the synthetic rubber. So for that, they developed this emulsion polymerization technique. So that means that emulsion polymerization is well known, okay, it's known since the 40s, since 1940s. Okay, the first physical descriptions of emulsion polymerization appear in 1948. Smith-Ewell made a very nice description. Okay, so from this point of view, emulsion polymerization is an old technology. It's a mature technology, actually. Okay, but there is still plenty of things. Initially, it was developed to produce rubber, styrene rubber. The polymers were styrene, the rubber that is used to produce tires. And in the tanks and the trucks, cars in the world need tires. So that was the main driving force to produce synthetic rubber. Okay, so these dispersions, which initially were rubber, nowadays the polymers that are dispersed in water are many different polymers with many different applications: coatings, paints, sealants. What else? Pharmaceutical particles for drug delivery, additives for concrete, blisters for pharmaceutical drugs also. I mean, there are many applications for textiles are also produced. Paper coating. All the paper that you have is coated with a thin layer of a latex, which is normally a cationic latex or a styrene also. So nowadays, emulsion polymers are used in a myriad of applications. Okay, so let's go to the point. So why is emulsion polymerization important, or which are the main advantages of emulsion polymerization? Okay, so first, emulsion polymerization, as I said, is a dispersion of polymer particles in water. As compared with homogeneous systems, where the polymer is dissolved in a solvent, the advantage is that low viscosity, because the viscosity of a dispersion is not given by the concentration of polymer, but by the size of the polymer particles and the concentration of the polymer particles, but not by the molar mass of the polymer. Okay, this is an important difference with respect to homogeneous systems. Low viscosity, therefore easy heat removal in large reactors, good temperature control, possibility to have high polymerization rates. Okay? It's a green technology. Already in the 40s, this was a green technology. No one claimed that was green at that time. But nowadays, we are concerned about environment. Emulsion polymerization uses water as solvent. Okay? So from this point of view, it's a green technology, environmentally friendly. It's easy. The monomers that do not react can be easily removed. The residual monomer can be easily removed. And this is the most important difference between the polymers that are produced by emulsion polymerization and any other technique. Okay? And is that in emulsion polymerization, it's possible to produce high molecular weights at high polymerization rates. Okay? This is impossible by any other technique. Okay? So we will discuss this with more detail later on, but this is the most important advantage of emulsion polymerization. So it's easy to make emulsion polymers. The dispersion can be used, as I will show you now, in the way they are produced as a liquid, or they can be coagulated and used dry. Okay? And the possibility of polymers is immense. The main disadvantage with respect to other techniques is here that we have impurities in the polymer. As you will see, we have to use surfactants or emulsifiers to stabilize this colloidal dispersion. Okay? So stabilizing this requires surfactants. Surfactants are a problem once you produce the film, because they migrate to the surface, they make more hydrophilic the polymer. Okay, the dispersion of polymer particles that we obtain in emulsion polymerization is called latex. And it's called latex because to the natural rubber, latex was the word that was used for the natural rubber. So now we can say that these are synthetic latexes. Okay, this is a dispersion that you will obtain in the continuous medium, which is water, which is this stabilized by surfactants, we will see now in a minute. The size of the particles that are produced, it can be produced in the range 50 to 1000 nanometers, so sub-micron scale. So we are also working with nano materials, okay, when we do an emulsion polymerization. But industrial products are in this range, between 80 and 300 nanometers. The solids content, the amount of polymer that we have dispersed in the water, in the commercial products, between 50 and 65, okay? Companies do not want to transport water at the price of polymer. So the higher the solids, the better for the formulation, okay? In the lab, at the research level, you can work at lower concentrations. The particles are mostly spherical particles, but normally they show a morphology, especially for new applications. We have more than one phase in the particles, so they are multi-phasic particles, okay? Different components, different arrangements, different morphologies. Okay, some figures to give you an idea that we are working in the nano world. If we have a dispersion in which half of the dispersion is polymer particles, 50% solids, and the particle size is 120 nanometers of these particles, average, because what you obtain is a distribution of sizes. But if this is the average, the number of particles that you have is 5 to the power of 17 particles per liter. Okay? But you can do this calculation. I will give you some time. Tomorrow you will let me know if you are able to do this calculation. Otherwise I will show you how to do the calculation. Okay? So try to do the calculation assuming that the particles are spherical. With this information, the particle size and the solids content, and knowing the volume of a particle, assuming that it's spherical, you can calculate the number of particles, and of course you can also calculate the area that the particles, the surface area of the particles have in 1 liter of this latex. As you can see here, 1 liter of latex, the surface area of the particles is 2.5 times 2 soccer fields. Okay? In 1 liter. So you have this area in 1 liter of dispersion. Okay? So the surface area that you have is tremendous. Okay? Because of the nanoscale. Okay? Of the particles. And the distance of the particles is approximately between 10 and 15 nanometers at this concentration, at 50% solids. Okay? This is a transmission electron micrograph of the dispersion. Okay? So this is what polylateral latex is. Okay. How the latexes are applied? 2 ways, as I said. We can apply the latex directly as latex, for instance in paints, coatings, where you apply the latex, normally formulated, not directly as it is obtained from the reactor. You add some additives, some other ingredients, pigments, and antibacterial products and things like that, or thickeners to obtain, for instance, a paint. But normally, as it is produced, you form a film. You apply, you let the water evaporate. I will show you now a nice video that shows this. The particles, as the water evaporates, they will pack in this hexagonal structure. And now, if the temperature at which we are producing this film is higher than the TG of the polymer close to the boundaries can interpenetrate, can diffuse, and the boundaries will be lost, and you will get a coherent film. Okay? So, but this only occurs if the temperature is higher than the TG of the polymer. If the temperature is below the TG of the polymer, you cannot make this interpenetration and you don't get good films. Okay? So this is one of the drawbacks of emulsion polymerization or emulsion polymers as compared with polymers in solution. Polymers in solution, when you cast a polymer in solution, you don't have boundaries. So the polymer in solution interpenetrates and the films are normally better than in emulsion polymerization. So there is plenty of research done on this, no? Because if you want to produce film which is strong mechanically, you normally need to use polymers with high TGs. But if you have high TGs, you cannot form film at room temperature, so you cannot paint. In Brazil, probably is. In other countries, it will be more difficult. Okay? So this is one of the ways to use it. The second way is coagulating the latex. When you coagulate, you obtain aggregates, and then these aggregates can be used in different applications. For instance, SBR, you can vulcanize this and produce tiles, for instance, or you can use impact modifiers for plastics. Sometimes, plastics which are brittle, you can introduce impact modifiers which are elastomeric, and you make the other polymer better. Or also dispersible powders. Cement, concrete, uses a lot of polymer and is used in this way. The powder is dispersed, redispersed in alkaline media with the concrete, and you will improve some of the properties of the concrete. Okay, this is the film. This is, let me see if I can show you this film. This is a video that shows how the films are produced from a latex. So this is how the particles move as water is evaporated. Okay? So the less water you have, the more slowly the particles will move, and they start packing. Depending on how fast you do the evaporation, you may achieve more order of the particles. If you dry too fast, the particles will be in any configuration. But if the drying is done slowly, the particles can organize in crystals, like you see here. So this is a slow evaporation. Now the coalescence will be shown. So you see, the particles are losing their identity. They are becoming a single film, but this, to be able to do this, the temperature should be higher than the temperature of the glass transition of the polymer in the particles. Okay? So, and you will end up with a coherent film where all the structure is disappeared. Okay? This is a demonstration film that was done by BASF. Which particles that can be seen in an electrical microscope. So these are large particles. I think the size is approximately above 500 nanometers. So that was possible to see in a video like this. Okay. Uses of emulsion polymers. Two ways. We said that the polymers can be used. Directly to film in the dispersed way or coagulated. Normally, half and a half. In the emulsion form, in the dispersion form, the main markets are, as you see, coatings and adhesives and sealants. 26%, 22% of the latex is used on that. But also in paper coating. Plenty of the latex in paper coating. Carpet backing. The carpets, in the back they have styrene butadiene, carboxylated styrene butadiene latex. Textiles also have, or non-woven also. Okay? So you see how this is distributed. These are numbers from 2012, but they haven't changed much. The total production of latex is at around 14 million tons in the world. So, in the coagulated fashion, SBR, ABS, styrene acrylonitrile, and PVC. PVC is produced by emulsion polymerization to produce plastisols, and also for jackets. It's used a lot. The polymers for the dispersions typically are acrylics, or vinyl acetate, the good glue, or the chewing gum. The chewing gum is polyvinyl acetate, okay? Ethylene vinyl acetate and vinyl esters. These are the most used polymers. Okay, so the polymers that are produced in these particles are characterized by several characteristics of the polymer. Some bulk properties, like the polymer composition. Imagine that you are polymerizing two monomers, like butyrachlate and styrene. So, depending on the composition, you might have a polymer which is tacky, so sticky, or you might have something which is non-adhesive, which is brittle. It has plenty of styrene. So, the combination of one and the other monomer, you can produce copolymers of the right properties. Or the chemical composition distribution, how the monomers are distributed in the chains. But the molecular weight distribution is also very important. As I said, we can produce higher molar masses in emulsion polymerization. So mechanical properties can be good. Branching, cross-linking. So these are also properties that we have to control. The particle morphology, the particle size distribution, and the surface composition. All of these characteristics of the polymers that are produced during emulsion polymerization, which defines the final properties. And not only one property defines an application property. Normally there is more than one property that affects. So this complexity of the characteristics of the polymer makes intrinsically appealing emulsion polymerization. The process is complex. The products that are produced are complex, but this provides a much more a wide spectrum of properties that can be produced and polymers that can be produced. Okay, this is a typical formulation that we have in an emulsion polymerization. Monomers, which are between 50 and 60%, and in any commercial formulation, you will have 2 or 3 monomers at least. Okay? One monomer will be hard. A second monomer will be soft. When I mean hard and soft, I mean that their polymers have high TG or low TG, so that you will combine hard and soft monomers to control the TG of the polymer that you want. Okay? And normally, there will be a functional monomer. The functional monomer can be an acid or can be a cross-linking agent, depending on how much you want to cross-link your polymer. And the acids are used because they provide also additional stability to the latex. Okay? Because with the pH, we can control if the acids are protonated or deprotonated. Okay? One thing, I'm seeing that you are taking pictures. I will give you this slides. So don't worry about this. No need to take pictures when you find something interesting. I will give you the PDF. I will pass to Claudia, and Claudia can give you the slides. Okay? So now you can listen and be more comfortable. Okay, so in addition to the monomer, you will have water, 40-45%, initiators, 0.5, surfactants or emulsifiers, depending, 0.5 to 3%, and we can have also chain transfer agents in the formulation to control molar masses. Okay? So this is the typical formulation. Let me go to the most important components, because the others you probably know. The chain transfer agent you know from homogeneous systems. The poroslinkers you also know. The initiators that are used in emulsion polymerization. Most of the initiators are thermal initiators, which means that they decompose with temperature. So at a certain temperature, the initiator will decompose and will create radicals. So normally, peroxides and azo compounds are used. So peroxides can be benzyl peroxide, terbutyl peroxide, terbutyl hydroperoxide, or persulfates, potassium, ammonium, sodium, in different systems can be used. Or azo compounds. So azo compounds, the more known one is AABN, isobutylolithyl, or AABA, which the difference between this and this is that this is oil soluble or more soluble in oil, and this is more soluble in aqueous phase. Here, this is water soluble, and this is water soluble. These are not really water soluble. the temperatures that you see here are the temperatures at which the concentration of initiator at this temperature reduces in 10 hours to half. So since we are working with water, these initiators are not appropriate for emulsion polymerization alone, because the concentration of radicals that they will generate will be too low at temperatures below 100, at which we have to work because we have water. Okay, so we cannot work at temperatures above the boiling point of water in emulsion polymerization unless we do it at the pressure. Okay, so suitable initiators are KBS, BPO, ABN, and ABN. So these initiators can be, as I said, water soluble and oil soluble. Water soluble initiators are preferred. Oil soluble initiators can be used, but water soluble initiators are preferred in emulsion polymerization. So you will have these radicals which are hydrophilic. They dissolve in water. They're persulfate radicals dissolve in water. This radical from the ABN is not water soluble. Okay, so this means that this monomer, this initiator will be in the droplets, and once it decomposes, it will go to the aqueous phase. But that's why these radicals, these oil soluble initiators are not that much used, at least industrially. In research, yes. Another type of radicals that are used, radicals or initiators, are redox initiators. So it's redox couples. For instance, persulfates combined with metabisulfite, you form a redox spread, and you will create, in this case, hydrophilic radicals. If you combine TBHP with ascorbic acid, you will produce turbotoxic radicals. Okay? The oxidant and the reductant, so the redox couple, and you can generate radicals. What is the advantage of the redox initiators? That you can generate radicals at lower temperatures. You don't need to go to 70 or 80 degrees. You can generate radicals at 40, 50 degrees. And in addition, the rate of generation of radicals is much faster with redox systems. Okay. The dispersion of particles that we create, as we discussed, has a huge surface area. So we said that 2.5 socket per liter of latex. So this dispersion of particles is thermodynamically unstable. So they cannot stay stable. In the Brownian motion of the particles, because of the temperature, if they approach, they will coagulate. So thermodynamically, a dispersion like this, with these characteristics, is totally unstable. So it will aggregate. Okay? So to maintain this stable, we need to have something on the surface of these particles. And this is what we mentioned, that we have surfactants. The role of the surfactants is to stabilize the polymer particles. Okay? So in another way, to create a barrier to avoid that upon Brownian motion the particles aggregate, so that maintain particles kinetically stable, not thermodynamically, but at least kinetically stable. To avoid this aggregation, we create a barrier here that maintains the particles stable in the atmosphere. And for that, we can use emulsifiers, which can be ionic, that they have charge, normally anionic surfactants, or non-ionic surfactants. Okay? So the surfactants or emulsifiers are amphiphilic molecules. An amphiphil basically is a molecule that contains a tail, a hydrocarbon tail, which is hydrophobic, non-soluble in water, but soluble in oil, and a head, which is hydrophilic, okay, which is soluble or happy in water. So these amphiphilic molecules can be ionic if the charge is negative, cationic, or cytheronic. That means that they have both positive and negative charge. Okay, it's a neutral in this case, and non-ionic too. Okay, these are the most common surfactants. Sodium dodecyl sulfate. This is the equivalent with ammonia as a cationic charge, and this is a cytheronic molecule, and this is a non-ionic where we have an alkyl chain, which is the hydrophobic part, and a polyethylene oxide chain, which is soluble in water. Surfactants have several functions in polymerization. The first one, what they do when we add a surfactant to water, the surfactant, since it is amphiphilic, it will go to all the interfaces that you have. Imagine this is a beaker where you have water. If you start adding surfactant, the surfactant first will cover the air-liquid interface. Of course, since the surfactants are partially water soluble, they will also solubilize. If you continue increasing the amount, it will completely cover all the interface. It will increase the concentration in the aqueous phase, and by doing this, what you are doing is decreasing the surface tension of the solution. Okay? It will reach a point in which all the surface is covered by surfactant, the solubility in water is occupied, and then the surfactants self-aggregate. Surfactant molecules self-aggregate forming micelles. And this occurs at a concentration that is called the critical micellar concentration of the surfactant. And this is a characteristic of the surfactants, the critical micellar concentration or critical aggregation concentration. So the surfactants aggregate, forming structures like this, spherical micelles, where the hydrophilic part will be towards the exterior, towards in contact with the water, and the hydrophobic will be towards the inside. And it can contain hydrophobic material inside. Sometimes, depending on the structure of the surfactants, you can produce also bilayers or vesicle or liposomes or even vesicles. Right? So there are different structures that can be produced. If we have polymer particles, imagine that you have polymer particles at a very low concentration, so that you have a stable without surfactant. I mean, if you dilute a lot and you clean the surfactant from your particles, and you start now adding surfactant to this solution, the way the surface tension will change is different. In water, in pure water, the surface tension decreases faster because there is no other surface that the air-water interface. But if you have polymer particles, the surfactant, in addition to cover this interface, will go also to all this interface. So you will need much more surfactant to be added to cover all the particles and to reach to the point in which you saturate all the surfaces and micelles will appear. Okay? So this difference in the concentration of the surfactant in pure water or in the presence of some particles will give you an idea of how much surfactant is absorbed into your particles. If you know the particle size, the diameter of your particles, you can calculate for each surfactant how much area does the surfactant hold. Okay? So this is what is, I mean, the curves that you may obtain by doing this analysis gives a Langmuir-like isotherm from which you can calculate this another important parameter of the surfactant, which is the parking area. It's called parking area, which basically means the area that the surfactant molecule or mole can cover. Okay? And this depends on the nature of the polymer that you have. Okay? And of course the nature of the surfactant. And we stop here. So we take a break now, let's say 10 minutes, 10-15 minutes, and then we start